So in this lecture, we're going to begin our discussion on a process in organic chemistry known as orbital hybridization. So let's begin with the following depiction. In our first case, let's suppose we have two different atoms. The first atom donates an s orbital and the second atom donates a p orbital. So these two orbitals will combine in a way to form the following molecular orbitals. So because we input 2, we should get back 2 orbitals, and that's exactly what we get. The first molecular orbital is known as the bonding molecular orbital. It's lower in energy. And the second one is known as the anti-bonding molecular orbital. It's the one higher in energy. So that's the first case. That's the normal case that we're used to seeing. So let's suppose we try a different thing. Now let's suppose we have a single atom, and that single atom has both an s orbital as well as a p orbital. What happens is, within that single atom, these two orbitals can combine in such a way to produce something that we know as hybridized orbitals. In other words, we have a single atom. Within that single atom, an s orbital interacts with a p orbital to produce two hybridized orbitals. Now once again, we input 2 orbitals, so we should get back 2 hybridized orbitals, and that's exactly what we see happen here. Now, when this s combines with this positive p, we get the following hybridized orbitals. In other words, this positive region simply combines with this positive region, and this becomes smaller. So a positive s orbital combines with a positive p orbital. The two greens combine, the blue becomes smaller to form an enlarged positive green lobe and a smaller or thinner negative blue lobe. And the same happens with when this part is negative. We get the following, because 2 negative lobes combine to form this enlarged negative section, enlarged negative lobe, and the smaller positive green lobe. Now in this lecture, we're going to only talk about sp hybridized orbitals. In future lectures, we're also going to talk about sp2 and sp3 hybridized orbitals. So what is an sp hybridized orbital? Well, this is simply an orbital produced using 50% s orbitals and 50% p orbitals. In other words, when we're combining our orbitals within that given atom, 50% comes from s and 50% comes from p. And this is known as an sp hybridized orbital. That's exactly what we have in this situation here. So let's look at an example in nature. So where is this evident? So let's look at one particular example in which a beryllium atom combines with 2 H atoms. So let's examine the electron configuration of beryllium. So beryllium in its neutral state has 4 electrons, 4 protons, 4 neutrons. So the electron configuration goes like this. We have 2 electrons that go into our 1s, and we have 2 electrons that go into the 2s. Now, we also have the 2 p orbitals, but since we have no more electrons, there are 0 electrons in the 2p orbital. So we can either represent it this way, or we can simply remove the 2p. Now, for my purposes, I'm going to leave it in this way, and we'll see why. So my question is the following. Will this Be donate a 2p orbital to bind with the H, or will it donate a hybridized orbital? In other words, which situation is more stable? So let's examine it this way. Let's draw out our pictures. Let's suppose that Be forms this hybridized orbital, and then this hybridized orbital interacts with the H atom to form our covalent bond. And let's also suppose that we have a beryllium atom that donates a simple 2p orbital to interact with that H atom. Let's see which one is more stable. Well, recall that whenever bonds are formed, bonds or covalent bonds are formed by the overlap of atomic orbitals, as we see here. And we know that the better the overlap, the larger the lobes, the more stable our compound is, the more stable our bond is. So in which situation do we have a more stabilized overlap, a larger overlap? Well, clearly, this case has a much bigger lobe, and that means the interaction will be much better in this hybridized interaction. In other words, this hybridized lobe creates a larger lobe, and that means because we have a larger lobe, we have a better overlap, and so that means this is much more stable, and so this will not occur. We're going to have this type of bonding. In other words, within this Be and H, when Be bonds to H, it creates a hybridized orbital which then bonds to the 1s of the H. And let's see exactly that in this energy diagram. So we can imagine this being the energy diagram. So the higher up we go, the more energy we have. The lower we go, the less energy we have. What happens is the following. The beryllium creates this hybridized orbital, sp hybridized, which comes from 1s and 1p, an sp hybridized orbital, and that orbital, which is a bit slightly higher in energy than our 1s of the H atom. So this is the H atom, and this is the 1s orbital, and this is the sp hybridized orbital of our beryllium. They will interact, so we input two atomic orbitals, and we get two molecular orbitals. So we get the one lower in energy and the one higher in energy. So once again, let's recap. So hybridization is simply a process that occurs within an atom. Within an atom, the orbitals can interact in a way to produce these hybridized orbitals that contain larger sections and smaller sections. The larger sections are able to better interact with other orbitals found on other atoms, and they produce better, more stable bonds. Now, we've only spoken about sp hybridized orbitals. In the next lecture, we're going to look at the sp2 and sp3 hybridized orbitals.